Fellow students, we are now into our second video lecture, and this lecture would be the last for this week. From next week we will have 3 lectures. Now this is because I gave you the 2 PDFs which I requested you to read, and as I have uploaded, I've also uploaded another PDF of the derivation of the Gibbs phase rule. So I think that's a good first week with a lot of work. Now we come down to this video lecture number 2. Now yesterday we talked about the thermodynamic phase. We discussed that rocks are composed of minerals, sometimes monomineralic, but mostly and almost always multimineralic. And each of these minerals have distinctive physical properties. They have well-defined boundaries by which you can separate a particular mineral from another mineral. And that these minerals have defined compositions. Say if you have garnet, or if you have biotite, or if you have quartz, or if you have calfelspar, their compositions are not unique. Each of their compositions are not unique, but their compositions vary over a definitive values. So this is what is a thermodynamic phase, and so all minerals are composed of these phases. The next point that we discussed that there are 2 kinds of phases. One phase which is called pure phase, or in thermodynamic context it's called a condensed phase. A condensed phase, that means a pure phase. So in the write-ups that I've sent you, part 1 is the thermodynamics of pure phases. Part 2 you will see, and which I will also do in more detail, much more details, is about solid solution phases. So we have 2 types of phases: monomineralic phase, one component phase, and multiple component phase. And these components, the phase varies over some span of range, of compositional range, and these endpoints are called end members. And so if you sort of mix them up in a homogeneous solid solution, these end members, there could be 1, 2, 3, 4, 5, 6, 10, there could be many, and these are defined as the end member phase components. End member phase components. And these end member phase components, when you mix them up, you can describe the chemical variability of the phase. So much so good. But there is another phase, and this I will discuss much later, which you don't see, which you can feel it's there, but you never see it. So when you look at a microscope, you really don't see that. What is it? Say, for example, your mineral is biotite. Now, if you analyze a biotite, 3.5 to 4% of it, 3.5 to 4% of it is composed of H2O, fluorine, chlorine, and so on. But you don't see it anywhere in your thin section or the rock that you're examining. Similarly, if you take calcium carbonate, for example, it contains a large amount of CO2, CaO plus CO2. It's a large amount of CO2, approximately 44% of CO2. So if you take a hornblende, and you will see if you analyze a hornblende that you will get about close to 2 weight percent of H2O. Close to 2 weight percent H2O. But if you take a chloride, for example, which is also a hydrous phase, maybe about 11.58% of it is H2O, fluorine or chlorine. So it's obvious that when the minerals formed, there was a fluid phase, but you don't see it now. So fluids are also treated as a phase. Yes, but it is a little more complicated than dealing with a non-fluid mineral phase. So we will do this fluid part of it significantly later. But for the moment, we will talk a little bit about phase components. So yesterday I talked to you about MgSiO3. So you can have more complications in your minerals. Say for example, let's take the case of garnet, for example, a mineral that you have heard about it. And a typical formula for garnet is that's a typical composition of a garnet. Typical composition of a garnet. This is the tetrahedral site, this is the octahedral site, and this is the cubic site. In the cubic site of divalent cations, Ca2+, Mg2+, Fe2+, Mn2+, and these are all trivalent cations, and silicon by itself is 4+. So from the garnet structure, you have 3 tetrahedral sites, which is almost always and invariably filled up by silicon, except in the case of hydroxyl. We don't go into that. And then you have 2 octahedral sites, which are filled by aluminium, ferric iron, and chromium. And then you have the cubic sites, which you have calcium, magnesium, iron, and manganese. So all these elements are competing for the 3 sites in the octahedral sites. There is no major difference. You see, there are 3 octahedral sites, so generally it has been found out that there is not much energy difference between all this cubic site. Similarly here, there is not much that affects thermodynamically. Macrothermodynamics, it does not affect so much. So they are 2 are almost equivalent, energetically equivalent octahedral site, and 3 energetically equivalent cubic sites. But this is what a normal garnet will contain. Have you understood? But say for example, chromium garnets typically are characteristics of high pressure garnets. This chromium is typically characteristic of high pressure garnets. Then say for example, ferric iron is characterized by garnets forming under extremely oxidized conditions. That means more near surface conditions. You know, you have deep inside the earth, you have iron metallic, that means it doesn't have a valency. Then you have Fe2 plus in a little more oxidizing states, and then you have Fe3 plus close to the earth's surface. So that is how the oxygen potential varies from inside the earth to the surface. And Fe3 plus garnets are mostly characterized from near surface situation. Right. So if we ignore all those complications, then we come to this Al2, Si3, and O12. So you have 2 octahedral sites, 3 tetrahedral sites, and here most garnets are Ca, Mg, Fe, and Mn garnets. But Mn is also an important component of some garnets, that's for sure. So if you look at this, then you have several types of garnets. So you have almandine garnet, you have grossular, you have pyrope garnets, you have grossular garnet, then you have spessartine garnets, If you take chromium, you have varovite garnets. If you have, what should I say? If you have ferric iron, then you have andradite garnets. So this is Fe3 is the key mineral here, andradite. Varovite is chromium, chromium calcium garnets. Spessartine is manganese garnet. Grossular is Ca garnet. Magnesium is pyrope garnet. Almandine is iron garnet. So these are the phase components of garnets. Phase component of a phase. So you have a phase component and you have a phase. So normally the custom, when you write something, say if you write garnet, almandine, So there is a way to write it, and this is internationally acclaimed. So you have X Fe garnet or X almandine garnet. Remember, the one in the lower case, as a subscript is the phase component. The phase component occurs as a subscript. And this is the phase. It's a superscript. This is convention. So if you take all phases and if you write the mole fraction of iron in garnet, that means the mole fraction in iron in garnet, or you could write mole fraction of almandine in garnet. Now look at this. This is written in lowercase. A is in lowercase, small a. Here, G, superscript, phase, capital letters. So this is the convention. Either you write down the formula or you write down the component name beginning with in the subscript in the lowercase, and the uppercase is always written with a capital. In this case, G. So what do you write for a pure phase? So X SiO2 in quarts. That's it. In this is equal to 1. Why? Because there is nothing except quarts. So here I write SiO2 up phase, I indicate the phase with a capital is equal to 1. Or you can write this way. Another more complicated way is to write Fe3Al2 Si3O12 in garnet. Now this takes a bit long. So what you do is you signify this as almandine, but you have to define what is your formula for almandine before. Have you understood? So you have to define before writing this that this is almandine. This is my formula for almandine. So this is an important step that we need to know. Phase and phase components, and there is something else with it. I will derive a small equation here, and it will give you a little bit of better insight into what I'm talking about. Now, in typically Gi phi, have you understood? Or G phi is equal to G as a function of pressure, temperature, N1, N2 dot Ni. This is what free energy is a function of pressure, temperature, and N is called the number of moles. Number of moles. So of a component 1, a component 2 to component I. So I is equal to 1 to n. I is equal to 1 to n. And this n is the number of moles. So like xn1 is equal to n1 divided by sigma ni 1 to n. Have you understood? So this is number of moles and this is mole fraction. What is mole fraction? xn1 is equal to n1 by sigma ni. xn2 is n2 divided by sigma ai, and so on and so forth. So this is how G is a function of pressure, temperature, and mole fractions, and the number of moles. If you remember now, if we go back and ask ourselves, we wrote yesterday G0, GPT is equal to G0 PT plus RT ln activity. This is what I wrote yesterday, if you remember from the last class. Actually, I remember first I write G is equal to G0 plus RT ln 1, and then I changed to GPT is equal to G0 PT plus RT ln 1 to tell you that this is at a particular pressure temperature condition. But a more accurate one would be G I P T phi is equal to G I 0 P T phi plus R T ln activity phi. This is the correct way. What have I done? From here to here, I have done is added I as a superscript. I as a subscript. That means I am talking about a phase component. Have you understood? And phi, what is this? A phase. Similarly, GI 0PT, phi is the phase. So, just to give you an idea, G Forsterite is equal to pressure, temperature, olivine is equal to G0, pressure, temperature, olivine, Forsterite, plus RT ln activity of Forsterite in olivine. That's how it is. You know, olivine has the formula, normal, very simple formula, MgFe whole twice SiO4, which means there are two components, Mg2 SiO4 and Fe2SiO4. This is called Forsterite and this is called Firelite. So, when I write this, I mean I'm talking about the Forsterite component of the system. Free energy of the Forsterite component of the system. Have you understood? I could have written a similar equation for G firelight, same, is equal to G firelight 0 PT olivine plus RT ln activity firelight in olivine. I could have written both. Have you understood? But I chose to write this expression just to give you an idea of what you should write. Here, when I write, I do not know what phase, what component, what nonsense. G of what? G of my head? No. G of a phase component in a phase. G, free energy of a phase component in a phase. Or you can write G, free energy of a phase. We will come to that later. Free energy of a phase. So now you see this equation. This equation. if I take activity equal to 1, then we are talking of a pure phase. Either fosterite or firelight, not olivine. We are talking of an olivine, but the olivine is either pure fosterite or it's a pure firelight. Right? We are talking about it. So, if you take this out, then the compositional term goes out. All compositional term goes out. So what you have is only this free energy as a function of pressure and temperature, but not of the compositions. But when I write it this way, it means I'm talking of a component in a solid solution. Have you understood? That is the most important thing. You have to specify in free energy whether you are talking of the free energy of the system, free energy of the mineral, or what are you talking? Or free energy of a phase compound. What? See, you see, thermodynamics is a very precise subject. It does not allow, once you know a little bit of thermodynamics, when you get into this thermodynamics, you don't have to mug up anything. It is very logical. There is nothing to mug up in thermodynamics. There is nothing to mug up in metamorphic petrology. There is nothing to mug up in igneous petrology. There is nothing to mug up in geochemistry. There is nothing to mug up in mineralogy. You've got to understand it, and that's it. Okay. Now, if I write the derivative, I am ignoring this phi, etc. It makes it a little complicated for you to see. So, just to make it simple, we are talking of free energy of a phase. Free energy of a phase at a particular pressure temperature and as a function of number of moles of the phase components, which is I is equal to 1, 2, 3, 4 to n, right? So, we are talking of the free energy of a phase in terms of its phase components. Now, if I find the derivative of this reaction, of this equation, then we can write this is how it goes. As a derivative of this is essentially you have the several partial derivatives. So essentially, if you take this expression here is given by minus S, which is called the entropy of the system. And this one here is called the volume of the system. And this one here, I will write it a little bit more clearly. Delta G by del Ni, this is called mu I, where mu free energy is called it's a free energy, and divided by N, this is molar free energy, and that is what is called chemical potential. So, chemical potential is equal to G by N is equal to mu, or dG by dNi is equal to mu I. Remember this. Gi by Ni, even if you make it even simpler, for you to remember it very simply. This is what it comes to. So the derivative of G by T is minus entropy, remember. Del G by del P is volume. And del G by del Ni by du. So if I write this, it becomes dG is equal to minus S dt plus V dP plus mu1 dn1 plus mu2 dn2 plus mu this is how it goes. So essentially what we can write is dG is equal to minus S dt plus VdP plus sigma mu I dni. I is equal to 1 to n. This is how I can write G. Minus S dt plus V dP plus sigma mu I dni, where I is equal to 1 to n. This is how it is. But I'm erasing this now. But free energy itself is equal to mu I Ni. This is G. So if I now So if I find the derivative equation, dG is equal to sigma mu I dni plus sigma Ni d mu I. This is another relationship. Now let me write this 1 and write this 2. G is equal to mu I Ni. Remember, mu I is equal to G by Ni. So G is equal to sigma mu I Ni. And if I find the derivative equation, it's sigma mu I dni and Ni d mu I. Now you see here, this both have same. So now I can write, equating 1 and 2, I can write sigma mu I dni plus sigma Ni d mu I, this is this part, is equal to minus S dt plus V dP plus sigma mu I dni. This is because dG is same, I put this equation. This is part of 1, this is part of 2. And if I do that, then you can see mu I dni, this cancels off. And so you get the expression S dt minus V dP plus sigma Ni d mu I is equal to 0. This is a fabulous equation. This is a fabulous equation. It's the beginning of chemical thermodynamics. It looks simple. It is not. It's a big philosophical equation. I am erasing this, it's not necessary anymore. This equation is called Gibbs-Duhem equation. It's called the Gibbs-Duhem equation. SDT minus VDP plus sigma Ni d mu y. Now, at isothermal isobaric condition means what? At isothermal isobaric condition means what? That means P is a constant because it's known. You have said that T is known. Therefore, dP is equal to 0. And P is also constant. Therefore, dP is equal to 0. If you apply this at isothermal isobaric condition, sigma Ni d mu y is equal to 0. Tell me, have you understood? This is important. No, you can't tell me. Okay, right. So, this is Gibbs-Duhem equation, right? Let's say this says the derivative of t, derivative of what are the variables? Let's say this is dt, dp, and d mu y. These are all the variables that you have. All the variables that you have. What does it relate to? A particular phase. The number of variables in a particular phase. That means it is the number of variables means what? Means the pressure, temperature, condition it is subjected. And the other variables. What are the other variables? The other variables are the mole fractions of the different components and mole fractions means moles, Ni, the number of moles of different components in the phase, and the free energies of those components in the phase. Say, for example, have you understood? What are the variables? dP, dt, Ni. What is Ni? The number of moles of phase component in a phase. What is mu I? Is the chemical potential. Remember, G by N it's also a free energy term. Well, it's also a free energy term, which is the free energy of the different components. So this equation connects all the variables that is affecting the stability of the phase. All the variables, temperature, pressure, the moles or the mole fractions, and the free energies of the different components. It's all linking them into one equation. At isothermal isobaric conditions, that's a known pressure temperature condition. That means T is constant, it's known. P is known. That means dt by dP is equal to 0. Then it says Ni d mu y is equal to 0. What does this mean? So now temperature pressures are not the variables because isothermal isobaric means pressure temperature conditions are known. They are known. So they are known. So the derivatives are 0. So this links the moles and the free energies of the different components in a phase. Let me tell it easily. Olivine is the phase. And there are two phase components, forsterite and firelite. So what does this Gibbs-Duhem equation do for olivine at isothermal isobaric conditions? Okay, let me write it for the full and then I will write it for this only. So for olivine, if I write this Gibbs-Duhem equation, it will look like S olivine dt minus volume of olivine dp plus, now you see, N of forsterite in olivine into d mu of forsterite in olivine plus N into firelight in olivine into d mu firelight in olivine. This is how it looks like. The Gibbs-Duhem equation of an olivine would look like this. If olivine also contains manganese, which it does normally, normally contains manganese, then you will have another component of manganese. So these are your variables. These are all your variables in olivine, and the Gibbs-Duhem equation links all it into one platform. Now at isothermal isobaric conditions, dt will be equal to 0, dp will be equal to 0. So if you take this, it will be N forsterite in olivine into d mu forsterite in olivine is equal to, plus N firelight in olivine plus d mu firelight in olivine, and this is equal to 0. I forgot the 0. I forgot to write the 0 here. So this is what happens for olivine at isothermal isobaric conditions. This is what happens for isothermal isobaric conditions for a simple binary solid solution. Now, if I bring this here down and write N forsterite in olivine is equal to then minus d mu firelight by d mu forsterite in olivine into in firelight. Now look at this. What does this tell you? Now you see here, I was here for not an isothermal isobaric condition. Then I change this to isothermal isobaric conditions, and now I write this expression. What does this expression tell you? It tells you a very important thing. It tells you that if you happen to change the number of moles of forsterite or X forsterite, say for example, or for example, if you know N forsterite and you know what is X forsterite? X forsterite is equal to N forsterite divided by N forsterite plus N firelight, right? So that is olivine, that's olivine, that's olivine, and that's olivine. So X forsterite is nothing but N forsterite divided by N forsterite plus firelight. Now you see here, so it's a very interesting thing. If you happen to change this, even at isothermal isobaric conditions, this will change. This has to change because this does not change. This does not change because this, for a pure phase, it becomes a constant ratio. So if you change this, one of the components, the other components need to change. But they should add up. They should be here. N forsterite plus N firelight, this has to change. So if you want to change N forsterite because of something, then you need to change N firelight. That means all these variables in this equation are not independent variables. They are independent as well as dependent variables. There are independent variables and dependent variables. Say, for example, x plus 5y is equal to 5. Now you see, if you put a value of x, independent variable, if you take a value of x, y is automatically fixed. Have you understood? If you change x, y will have to change. So x is the independent variable, y is the dependent variable. Look at here. If you want to change this, if you want to keep it at a particular value, this is fixed. This is fixed. But if you want to change this, this has to change. This has to change. Now that is very important to tell you that Gibbs-Duhem equation essentially what it does it links all the variables including temperature, pressure and the different moles into one single equation. But all the variables here are not independent variables. There are also dependent variables. Just like x plus 5y, if you put x is equal to 2, then y will have a fixed value. Y becomes a dependent variable. You can't change, if this equation is true, you can't change both x and y arbitrarily. It fixes according to the equation. Similarly here, if you change phosphorite, firelight will not change arbitrarily. It cannot change. It's fixed by this reaction, by this equation. You can't change it arbitrarily. So one, if it becomes an independent variable, other becomes an independent variable. It has to change as controlled by the particular equation. So, this is one important thing about phase components. And between phases and phase components. A phase can be written in part, as always, by a Gibbs-Duhem equation. In a Gibbs-Duhem equation, the variables are temperature and pressure, as well as the phase, as well as the number of moles. Have you understood? So, but all of these variables are not independent variables. There is independent and dependent variables. So all of them are not independent. You don't need to quantify all variables. One or the other two variables will always be dependent. Right. So the accompanied write-up that I have given you for the derivation of Gibbs phase rule essentially depends strongly on Gibbs-Duhem equation, although it's not said. But now if you read that particular write-up that I will give you, you will see that this is a very important equation that they use. Chemical potential, Gibbs-Duhem equation, and mole fraction. Remember, in a mole fraction, say for example, in this equation, x phosphorite, if you find out a particular way of x phosphorite, then x firelight itself becomes a derivative, becomes a dependent variable. Because x phosphorite plus x firelight is equal to 1. So if you change 1, the order is automatically fixed. These two terms, Gibbs-Duhem equation and mole fraction equations, are intertwined in finding out the Gibbs-Duhem in terms of the Gibbs phase rule. In the next class, we will talk about Gibbs phase rule. We'll start with Gibbs phase rule. But before that, before to end this class, I will just try and introduce you. We have talked about what is called a system. What is called a system. We have talked about a phase, and we have talked about phase components, and we have talked about how phase and phase components phase components and other variables are integrated into the Gibbs-Duhem equation. We are left with one important thing. It's called components. When said this way, components are two. One is called a phase component and the other one is called a system component. A phase component describes the chemical variability of a phase in a system. Or A phase component describes the chemical variability of a mineral in a rock. But when you talk about system component, then you need not to talk about only one mineral, but the whole rock, which could be multimineralic. So that is what is called a system component. So when somebody says component, it essentially means system component. It essentially means system component. Otherwise, the right way is to say system components and phase components. They mean completely different things. Now say, for example, what is a system component? Now, the ideal definition is the minimum number of molecules or minimum number of molecules or components of a system. Chemical variability of a system. It is the minimum number of components that describe the chemical variability of the system, or minimum number of formulae that describes the chemical variability of a system. That is what is a system component. Now let me explain. Say I have a mineral Al2SiO5. I can write it as 2Al plus 1Si plus 5 oxygen. I can write it. Or I can write it as 1 Al2O3 plus 1 SiO2. Or I can write 1 Al2SiO5. This I can express in the three ways. If here I write it this way, I require three formulae. If I do it this way, I need two formulae, SiO2, Al2O3. Here, AlSiO. And here if I take, then I take one formula. 3, 2, 1. Now, according to the definition of a system component, it is the minimum number of components or formulas that describe the chemical variability of a system. So, if I take that definition, then this is correct. Because this is the minimum number of components that describes the chemical variability of the phase. But, so, Al2SiO5 can be described only by one formula. That is Al2SiO5 only. So, it is a one component system. One component system. Phase, if you ask me phase, I said you told me a formula. Now you are asking me phase. You tell me the phase. You ask me a formula, I am telling you this is the phase component. This is one. Which phase, how many phase, that you tell me. So say for example, if you have the Al2SiO5 pressure temperature condition and you have this, so you know this is silimonite, this is andalusite, this is kyanite. All of them have the same formula, Al2SiO5. Now, whether it's kyanite, whether it's only silimonite, Al2SiO5 will have one phase component. If it's only kyanite, it will have one system component. If it's andalusite, it will have one phase component. If it is andalusite and silimonite, that means you are lying on this line, andalusite and silimonite together. along this line, it's still one component. If you have kyanite, sillimanite, it's still one component. If you are here, where andesite, sillimanite, and kyanite, all three should be in equilibrium. All three should be in equilibrium. The component is still one. Right? That's a very, very important point that I want to make. So this is what is important about system components. Say, for example, just this, and after that we will. Now you see how this changes. Say, you know, if you work in low-grade metamorphic rocks normally, you see a lot of veining. These are very famous. These are called, don't ask me why they form in a completely different way. There is something called sillimanite quartz veins or kyanite quartz veins. These are veins that intrude the rock. They are not metals because at such low temperatures you don't heat the rocks. They are formed due to some process and we ignore the process. But there could be a rock where you have sillimanite and quartz. So you know whether it is sillimanite or kyanite, it does not matter. Let's say the formula is Al2SiO5. Let's say the formula is Al2SiO5. It's an aluminum silicate. And you have quartz. So now you have a two-phase system. Could be three. If both sillimanite kyanite is there. If sillimanite kyanite and andesite also is there, then it's a four-phase field. But whatever it is, it has an aluminum silicate and it has a quartz. Now what will be our phase component? This is Al2SiO5 and this is SiO2. Quartz is SiO2. So how many phase components? We can do it by writing, you see, I can write in terms of Al, Si and O. I can write like before, 2 Al, 1 Si, 5 O, and this one, 1 Si and 2 O. So I can take this, or I can write Al2O3 and in terms of Al2O3 and SiO2. So this will be 1 Al2O3 plus 1 SiO2, right? And this will be 0 Al2O3 plus 1 SiO2. So this could be another possibility. Here there are 3 components, here there are 2 components. But if I take Al2SiO5, then I can write this as 1 Al2SiO5, but I don't have anything for SiO2. I don't have anything for SiO2. So here the best is, this is out of question. We are left with AlSiO, 3 system components, or Al2O3SiO2, 2 system components. And you would say minimum number of components. So it's a 2 component system. So this is acceptable. Not this, because it's too many. And this, because it's too less. This is correct. Al2O3 and SiO2. Now just before we conclude, I can just tell you this. I could, instead of taking this, I could have also taken Al2O3 and Al2SiO5. Sounds strange, huh? But no, it's right. Thermodynamically perfect. Thermodynamics does not understand these ones. It understands numbers. Al2O3, Al2SiO5. And you will see, what's happening? Very simple. Al2SiO5, how will you write? As 0 Al2O3 plus 1 Al2SiO5. And you have SiO2, you will write as minus 1 Al2O3 plus 1 Al2SiO5. Done with? Yes, it's right. So here also 2 components. This is equally valid. Also equally valid is SiO2 Al2SiO5. equally valid. So all these three, 1, 2, and 3, all are correct. So long the number is 2. Rest, it doesn't matter. You can have L2O3 SiO2. You can have L2O3 L2 SiO5. You can have SiO2 L2 SiO5. Doesn't matter. But you can't have AlSiO, 3 component, it is wrong. And you can't take L2 SiO5 because you can't describe the formula of SiO2. So essentially, if you take this, you see, if you take this is the composition of this one, and this is the composition of quartz. So it's a 2-component system. Phase, that depends on what is there. So long its formula is Al2SiO5. So long its formula is SiO2O5. Okay, I think I will stop now. Yeah, I think I must tell you the following thing, that you've got to understand things. You can't mug it up. Don't mug up. I always tell when I'm taking a physical class, when I used to take physical class, for my examination, for my course, the night before you go to a discotheque. If you haven't studied so far, you aren't going to do much. Don't read the last night. It's no use. And if you read before, it doesn't matter, you go and dance. If you have understood it, it doesn't matter. That's the very important thing that I'm trying to tell you. Try to understand. You've got to give time to metamorphic petrology. You've got to let things sink into your heart. Don't try to mug up. You will go nowhere. And you see, this is difficult times for you and me. And I have to set you questions. And we will have 2 or 3 class tests. I've not figured that out still. I'm still worried about your laboratory class, which to me is a big, big pain. We will break it up into 3 tests, 3 class tests. All of them will be open book class tests. Open book class tests. You know, I don't know ever in your life if you have answered open book questions. I had done it when I was a student. They're tough. Even if I try to make it simple, it can't be made simple because you have too many things around you. And if I have to test you, I have to go off from what the book says. That would require you will have to be very thorough in what you're studying. I'm not trying to set panic. I'm only trying to say, be very serious with my course. People get excellent in physical classes. People also fail. So you have all the extremes. It's left to you as to what and how you will tackle this. But the only way I can tell you, there are many books now available. Say, for example, books by Philpotts, the book by Winter, and some other Xeroxes. I will continuously give it to you like I've given. I will continuously applying with the Xeroxes. And there are many, many internet sites which deals with it. So I think you have enough time and you should concentrate on the subject. It's not going to be easy. First of all, metamorphic petrology is not a subject that it's not for the weak mind. And secondly, for an open book question, you've got to be thorough with what you're learning. Right? Thank you.